flywheel.
Fine.
Okay. If you have a sequence of IID of random variables with what? With finite expectations. By the way, you can also essentially prove that if they are identically distributed, their expectations and their variances will also be equal actually. Okay? Because think about it. If x1 has a CDF f1, so the density is small f1, then think about it. So I have expectation of x1 equal to x over the entire, whatever my space is, multiplied by the PDF of x1. Okay? And since, think about it, since this expectation, since this PDF is equal to the PDF of xn of x actually, for any xn, because the CDFs are equal. Okay? So if the CDFs are equal, you differentiate on both sides, the PDFs are equal. So in other words, if I compute, for example, expectation, which is x, okay, fx1 of x, then this must be same as an f, and the PDF of x1 is same as the PDF of xn, so this guy would be the expectation of what do you call xn. So in other words, one of the corollary of this would be that if you have independent and identically distributed random variables, their expectation and variance would be same actually. It would be the precisely same number, one number. Okay? So
will there be anything that will be different?
I'm sorry?
Will there be anything?
Yes, they can take the different value. They are different random variables. I'm not saying that they are equal to each other. In other words, you can have, for example, here's an example. So I can have, KFC, okay? So, and this is kind of representing, this is time interval, and this is representing the people that are visiting KFC. Okay, so like 8 p.m. it's peak, and in the morning it's there are less people, in the late night there are less people. And I can say that there is what you call Hori score, for example. So it can also have a similar kind of a distribution. Okay, that you have peak at these timings, and then the beginning and the last you have what do you call less people visiting this place. So they follow same distribution, but they are different two quantities actually. Okay, are you getting the point? So they are representing two different phenomena. So in other words, when we say that two random variables have same distribution, does not mean they are equal and identical. They are representing the same quantity. No, they can be different. They can be entirely different. But being IID means that okay, if you know the distribution of the one of the random variable, you know the distributions of all of the random variables. Okay. Alright, so the theorem is basically so-called weak law of large numbers. Okay. Weak law of large numbers. So it says that if you have a sequence of IIDs with expectation of xi equal to m, that is finite, okay, and variance of xi being one number sigma square for I equal to 1, 2, and so on and so forth. In other words, all of these random variables has a finite mean and a variance actually. Not assuming variance to be finite actually. Okay, maybe finite expectation and variance. So maybe they are finite. Okay, they both are finite. Okay. Then what we can show, take a partial sum of this sequence. In other words, take say the first n terms of this sequence and compute the average of it. Okay? Where I is running from, okay, what should I say? I here, k here, where k is running from 1 to n. Okay, so it is the average of first n random variable. Okay, so what we want to prove is that this average is going to converge to the mean m.
M is between.
Okay, and the same average, and hence actually I will also say that okay, this converges in what sense? In L2 sense. Okay, and hence I can deduce, if this is true, that the average, okay, the average converges also to this mean in probabilistic sense, in probability. Okay, so if we can prove this, this would be obvious because we know that convergence in L2 implies convergence in probability. Okay, so what the theorem is telling you? Theorem is telling you, imagine you have a sequence having, they are identically distributed, having the same mean and the same variance, and you take the average of this sequence. So this average is going to have an average that is going to converge to what you call the average of the entire sequence actually in L2, and hence in probability. Okay, so this is what essentially what you call weak law of large numbers is. In other words, okay, so you know this information, they have a particular mean, and you take the average of the sequence of these terms, they will also converge to the same mean as whatever the sequence is following. Okay, so let's try to prove this result. So in order to prove this, what we need to do is simply, so it's just a one-liner proof actually, it's not really, much can be said about the practical importance of this. Okay, that what are the practical importance of this? This is a beautiful theorem, giving you insights about this information about the sequence of IIDs actually. Anyway, so what would be the proof of it? For the proof, in order to prove this convergence, what I need to do, I need to compute the difference of this and m and its L2 norm actually. So in other words, I need to compute the expectation, okay, of this sum of xk, where k goes from 1 to n over n minus m square. Okay, I need to show that this goes to 0 as n goes to infinity. In order to show what I need to do, I need to, okay.
Sir, expectation under absolute number.
I'm sorry?
Difference.
But the absolute of the square is same as without absolute, so it's not a big deal. With the square, you can get rid of the absolutes as well. Okay? So, what can I do? This is what that I would like to compute. Okay. So let's first compute the expectation. So okay, let's call Sn as this sum actually. So let's give this sum a name. Sn is k equal to 1 to n and xk. Okay. By the way, what would be the expectation of Sn? The expectation of Sn is going to be the expectation of this guy. Okay?
So linearly on the
yes, so it would be k equal to 1 to n and expectation of xk. So this would be simply mn actually. So we are summing mn times. Okay? And if I, for example, divide both sides by n, in other words, if I compute the expectation of Sn over n, So this is same as M actually.
Apply.
Okay. How about the variance of the random variable? Okay. So with this conclusion, now let's get to this expectation actually. Okay. I'm creating a mess. Let's do it. So I want to compute this Sn over n. So this is this quantity Sn over n minus m, and this is square m. That's what I would like to compute. Now, this guy is saying miraculously, this will be same as variance of Sn by n. The question is why? Can we see it? So let's compute the variance of Sn by n. So the variance of Sn by n is going to be the variance of this sum. I can okay, 1 over n square, k equal to 1 to n, and xk.
Sir, directly we can do so. Consider Sn over n to be a random variable. You have its expectation there.
Okay, so it's a by definition. Oh, we shouldn't. Okay, so we shouldn't do this. But this is the definition of basically the variance of Sn, because what is variance? Variance is that take the random variable and subtract its mean and compute its square of expectation actually. So you get this. So this is precisely the variance of Sn. And therefore, but now I can explicitly compute this variance. So if I want to compute the variance, I need to compute the variance of this sum actually. Okay, that's sum Sn by n. So this would be same as computing the variance of xk, where k runs from 1 to n, and everything divided by n square. So in other words, you can pull this 1 over n outside of the variance, then it will be squared, and the variance of the sum is basically sum of the variance, not in general, but for independent random variables actually. Otherwise, you have to subtract the covariance in it. Okay, but since the covariances are 0 here, so you don't need to do that. So in other words, the variance of the sum of two independent random variables is equal to the sum of the variances. Okay. So what would be this guy? So this guy would be, okay, k equal to, so this would be, if I compute it, it would be n sigma squared by n squared. Right? So therefore this would be sigma squared by n, and obviously this goes to 0 as n goes to infinity. Okay? So in other words, this average of this average as n gets bigger and bigger will converge to what do you call that? The average of the sequence of the random variables actually. Okay? Well, this is obvious because we know convergence in N2 implies, the convergence in probability. So, this is what you call, so there are three basic, there are many basic limit theorems, but if you say the first three basic limit theorems are what? The weak law of large numbers, strong law of large numbers, and central limit theorem. So our task today is to prove at least some of these actually. Okay? So this one is easy. The central limit theorem is a bit trickier. If we want to, for example, prove it in entirety, because it requires a lemma. But in order to prove that lemma, you have to prove lots of other results actually. So the proof of central limit theorem is not difficult. Okay, you can teach it even to, what do you call an FSC student, because what you only need is basic calculus actually. But the lemma on which the central limit theorem is brought, it's a serious result actually. So what I want to do, I don't want to prove the central limit theorem directly by assuming the lemma, but I will try my best to reach to the lemma actually, or the proof of the lemma. I'll try to give you all sufficient necessary background to prove that lemma, and then you can prove it for yourself, and then we can use it to prove the central limit theorem. Anyway, so in order to proceed further and to prove the central limit theorem, I need to define what do we mean by convergence in distribution. So it's another kind of convergence. So we have seen different kind of convergence. So convergence in measure, LP convergence, lots and lots of type of convergence. So what I want to do is basically define what we mean by the convergence in distribution actually. So pretty simple definition. We'll do one example and we'll prove one linking result. So the definition is that if we have a sequence of random variables, let xn be a sequence of random variables, not necessarily IID or any other thing, and x be, so xn be a sequence of random variable and x be a random variable. Okay, so I'm writing it, but you may assume it. Then we say that this xn converges to x in distribution D. This is also called the convergence in low. Okay? So convergence in distribution or convergence in low if every point x where the distribution function of x is continuous, okay, we have what limit y goes to x of if limit n goes to infinity, f xn of x is equal to f of x, f x of x. Okay, is it making sense? So what does this mean is that we have a sequence of random variables, so obviously you're going to have a sequence of distribution functions. So you have a random variable, you will have a distribution function. So that if the sequence of distribution functions is converging to sequence to the distribution function of x, not at all points, it's not a pointwise convergence, okay, but at those points where fx is continuous. Are you getting the point? So in other words, if x is a point for which f of x is continuous, at such points you have this basically convergence, you're going to say that xn is converging in distribution to xn. Is it making sense? By the way, I'm sorry? Convert D. So descents are distribution are in low actually. Okay? So some people like to write low. Even some people like to call this weak convergence actually. Some people also call it weak convergence. Okay? Okay, so there is a slight difference, but okay, you can also interpret it in this manner. Is it making sense? So take the sequence of distribution function, take x, take the distribution function of x, see at what point this function is continuous. At those points, if the sequence of distribution function of xn is converging to distribution function of x, of the random variable x, if yes, the sequence is converging in distribution to what do you say, x or converging in low. Okay? Let me do one example and then do one result.
So what about continuity of f of xn, fxn?
I'm sorry?
What about the continuity of fxn?
We don't require it at the moment.
It can discontinue. Then how would we evaluate it?
Okay. Do we need continuity?
Otherwise we can't evaluate it. We can evaluate without continuity requirement. Yes.
In other words, okay. Doesn't say in the definition,
Yes.
so I can't assume it. So maybe we don't need it. We'll prove some results, maybe we don't need it. Let's do an example. Here's an example. Let x be a standard normal random variable. Okay? And define xn in this manner. That xn is x if n is odd. Okay, and it's minus x if n is even. Okay? And the claim is that xn converges to x in distribution. That's how. By the way, if x has a distribution, so start with an observation. If x has normal distribution with mean 0 and 1, what would be the distribution of minus x? So it would be obviously normally distributed. Changing the sign is not going to change the thing. But what would be if the expectation of x is 0, then what would be the expectation of minus x?
0.
Must be 0. If the variance of x is 1, what would be the variance of x? 1. So minus x is also normally distributed. Okay?
So what would change the but?
I'm sorry?
What thing would change? I'm not getting this thing. It would have the same distribution.
No, they have the same distribution, they have different values actually. So think about it, x and minus x as, an output as a function, so if x has some definition actually, then minus x is different from x actually, with a minus sign different. So obviously we want to do a simple example, not too much complicated. Okay, so if this is the case, then I can say that what is the distribution of xn? In general, no matter what happens, it's normally distributed with mean 0 and 1. Okay? Why the xn is going to converge to, what do you say, In other words, can we have such kind of an inequality? So let's think about, so let's compute limit n goes to infinity, okay, of fxn of x actually. So the xn of x is the probability that xn is less than or equal to x. Okay? And how can I compute this probability? So I can compute this probability by integrating from minus infinity to x actually. Okay? You know, integrating what? The PDF of basically xn, and the PDF xn is?
Sir, wanted it from 0 to...
I'm sorry?
It's distributed from... No, I'm sorry, I was wrong.
Okay? So this would be what? So it is going to be, okay, normal, what is the PDF of xn? So it's
Small
simply e to the minus t square by 2 over square root of 2 pi dt. So you have it basically. Okay? But what is fx of x actually? This is precisely equal to this quantity. Isn't it? So what would be fx of x? So the probability that x is less than or equal to x, which is equal to this entire this. Okay? So in other words, they are equal even without limits actually. So even if you take a limit, this would be still true actually. Are you getting the point? So the inequality is trivially true. So you can say that xn is converging to x in distribution. Okay? So I would like to prove a theorem, after which you can find even more lots and lots and lots of examples of convergence in distribution. Are we still not happy with this? I mean, if we are not, we just do ask actually. I'm saying, you know, forget about this limit. Just compute this is equal to this. So the CDF of this is going to be also equal to this.
इनका कोई रूल नहीं.
I'm sorry?
Integral में इनका कोई रूल नहीं.
And का कोई rule नहीं, because all have the same distribution, whether it's negative x or positive x, it has the same distribution. No, लगा भी दें. So what I'm saying is that okay, so they are equal to each. So it's like a constant basically sequence actually. So the constant sequence always converges. In other words, you take
The value
limit, you know, you're still gonna get the same thing. Okay. One of the key results that I would like to prove is basically this, that if a sequence is converging in probability, it must converge in distribution actually. So all those sequences that converge in probability must also converge in distribution. In other words, the weak law of large numbers that you proved is also basically true in the sense that it's also true in the sense of distribution, sense as well actually. In other words, this average converges to M in distribution as well, because the average converges in probability. So anyway, so how to prove it? The proof is a bit interesting, okay, and it's a test of your real analysis. Let's see that how much of real analysis you still remember. At least, I'm sure Yunus remembers some of facts basically. So what we have is basically this, and this is what that I would like to prove. Let's see. So let's assume that x be a point of continuity of fx, okay? Because that's the point I would like to play at. And what we would like to show, we would like to prove this basically result that the sequence of distribution functions of xn is converging to the distribution function of x. Okay? In other words, we want to show that this probability, which is xn less than or equal to x, which is basically xn of x is equal to fx of x, which is same as probability of x less than or equal to x, okay, as n goes to infinity, not equal to that.